Hi, welcome back. We've been talking about continuity a lot, and we've got two different definitions of continuity in play here. We've got sequential continuity, which is the top definition there, and epsilon delta continuity, which is below it. Today, we're going to prove that these two kinds of continuity are equivalent to each other. Any function which is sequentially continuous at a point x naught is epsilon delta continuous at that same point, and vice versa. I want to remind you what sequential convergence means because we're going to be using this fact. We're going to start with this direction. If f is epsilon delta continuous at x naught, then f is also sequentially continuous at the same point x naught. So this proof is not difficult, but ties together so many different ideas that it might be a little confusing. So we're going to prove it directly and naturally, sort of in paragraph form. And then I'm going to pull it apart using a little bit of proof theory to illustrate what's really happening here. So if you understand the first thing completely, then maybe the proof theory is not necessary for you. But if the first statement here is going to be a little bit complicated, then it might be worth pulling out and showcasing all of the details of what's really going on in this proof. So we have two directions to prove here. One implies the other implies the one. But instead of doing both directions, we're going to do one direction twice here. Once sort of natural language and once a little bit more formal. So let's get started on this. Of course, we're going to assume that f is epsilon delta continuous. I'm just going to abbreviate continuous CTS, continuous at x naught. And then we need to show that f is sequentially continuous at x naught. And what does sequentially continuous mean? It means whenever the limit of an is x naught, then the limit of f of an is f of x naught. So let's let an be a sequence in the domain of f. And we're going to assume that the limit of an is equal to x naught. OK, so that gives us a sequence there. And now we want to show that the limit of f of an, so the goal is the limit of f of an is going to be equal to f of x naught. Now, this is a limit proof. I mean, this is a limit, but that's an assumed limit. This that we're trying to prove is a limit, and so we're going to prove it by the definition of the limit. So for that purpose, what we're going to do is we're going to let epsilon be greater than 0. Now, I have no idea how to choose the cap n that I need, at least not yet. But I do have an epsilon greater than 0. And I also have an assumption of epsilon delta continuity. And so what I'm going to do with that is I'm going to choose delta for epsilon in the definition of the epsilon delta continuity of f at the point x naught. And then I want to illustrate what we've really done here. We've chosen a delta for epsilon, and then what do we know? So what we know about that is for all x in the domain of f, if x minus x naught is less than delta, then f of x minus f of x naught is going to be less than epsilon. So that's what it means to have chosen delta for epsilon in the definition of the epsilon delta continuity of f at x naught. And so now we have a delta, and notice that I am really interested in demonstrating that x minus x naught is less than delta, but I also have this limit. The limit as n approaches infinity of an is equal to x naught. And so what I'm going to do is I'm going to use this delta as if it were an epsilon in the definition of the convergence of an to x naught. So now I'm going to choose n for epsilon equals, well, I'm going to choose n for delta in the definition of the limit of an is equal to x naught. So I'm choosing n for delta. Now, that might be a little bit confusing. I want you to read this definition as it applies to an equals an and a equals x naught. Then this says for every epsilon there exists an n. But that's any positive value epsilon, right? And so long as this is so long as we have a positive value to plug in here, we may choose an n so that the rest of this is true for that positive value epsilon. The positive value that I want is the delta that I have just chosen up here. And so I'm going to basically, for epsilon, I'm going to plug in delta. And then this is going to give me a statement of the form, little n greater than cap n implies something is less than delta. So we're going to choose this n. Now notice that we have now chosen an n, right? The definition of sequential continuity, the definition of the sequence limit f of an equals f of x naught demands that we should let epsilon be greater than 0, and then we should choose an n. And so a lot of stuff has happened in an intermediate sense, but we have let it epsilon be greater than 0, and then we have chosen an n. And so let's hope for the best here and continue with the definition, with the structure of a proof of continuity. No, sorry, with the structure of a proof that this limit is equal to this value. And how would that go? We're going to say then let n be greater than n, right? That's the next step in a proof of a sequence limit. And then what will we do next? We're going to examine f of an minus f of x naught absolute value. And that's the thing which must be less than epsilon. So is it? Well, let's find out. So actually, I think I probably shouldn't write it yet. I think it's a little premature for me to write it down. So if n is greater than cap n, then what do we know about it? Well, we've chosen cap n for delta in the definition of this limit. And if n is greater than the cap n chosen for delta in the definition of this limit, then what we know for sure is that an minus x naught is less than epsilon. Is it epsilon? No, it's not actually epsilon. We've chosen cap n for delta, so we know that this is less than delta here. So basically, because we've chosen cap n for delta in the definition of this limit, when n exceeds that, then we know that this is less than delta. Now, here's a value less than delta, and it's of the form something minus x naught. But notice that, where is it? Because we've got delta chosen for epsilon in the definition of epsilon-delta continuity, whenever any x minus x naught is less than delta, then we get an equation like this. So basically, because of this implication here, we get then f of x minus f of x naught is less than epsilon. I made a mistake here. So this is true generically for any x in the domain, but this assumption applies to an in particular. And so it is for an in particular that we know that this equation is true when x equals an. And we should deduce the corresponding equation when x is equal to an. And so I should write f of an minus f of x naught absolute is less than epsilon. So now let's look what we've done here. We've let n be arbitrary. And then, yes, there's intermediate work, but then we have shown that if n is greater than cap n, then we get this equation. So basically, we took an arbitrary epsilon, we did some intermediate work, and we chose a cap n. We let n exceed cap n, and then we proved that this difference was less than epsilon. This is the correct proof structure for a demonstration that for every epsilon, there exists a cap n, such that for every natural n greater than cap n, then this equation holds. In other words, this is the correct proof structure to prove that the limit of f of an is equal to f of x naught. And so we can conclude here that the limit of f of an is equal to f of x naught as desired. Now, that means, so what have we got here? We've got an assumption that an converges to x naught, and then we've proven that f of an converges to f of x naught. And an was arbitrary, and so this is always the case, and so that means that f is sequentially continuous. So f is sequentially continuous at x naught. And that demonstrates that if f is epsilon delta continuous, then it is also sequentially continuous at the same point. Now, if that proof is making your head spin, well, let's make it spin a little faster. What we're going to do is I want to present to you, so for two reasons here. I want to make this proof clearer, but I also want to show how this proof can be expanded and sort of torn apart using some proof theoretic thought, because I want to showcase a little bit of proof theory as well. And so what I want to do here is I want to pull this proof apart and talk about it in the context of proof theory and talk about what's really happening here. So what we're going to do is we're going to start over from the beginning here, and we're going to think about this on the level of how proofs work, generally speaking. And this is a fairly complicated proof, and it's easy to get lost in the middle of the details here. And so I think bringing a little bit of proof theory will give it a little bit of structure and will help us understand what it's really doing. However, it's going to be a little bit longer this way. So this is the official proof that you might see in a textbook, or I might expect you to write on a homework or something. But what we're going to do here is we're going to pull this apart even more and give an explanation of what's really happening that goes a little bit deeper into the detail. So let's do that. So again, we're going to prove the same thing. I'm not proving the converse. I'm reproving the exact same thing. And in a sense, I'm giving the same proof. I'm just going to present it differently. So let's give the same proof again. So proof. So let's identify what it is we want to show. So let's say to show. To show. So F is, I'm going to use some abbreviations here because it's going to be, there's going to be a lot going on. So F epsilon delta continuous implies F sequentially continuous. Okay, that's what we want to show. And so we're going to begin here with an assumption that F is epsilon delta continuous. I mean, what could be simpler, right? If you want to show P implies Q, you assume P, right? So we're going to assume that F is epsilon delta continuous. And now let's immediately write the content of that assumption. So I'm going to put a colon here, and I'm going to write the content of that assumption, which is for every epsilon greater than 0, there exists a delta greater than 0, such that for every x in the domain of F, if x minus x naught is less than delta, then f of x minus f of x naught is less than epsilon. Sorry for writing small, but I don't have a lot of room here. So that's the content of the assumption. Now, under this assumption, so why did we assume this? Because we're proving an implication. So in the context of that assumption, then we have a sub-goal. And let me write to show because it's the same thing as before. So we have a goal here. And that goal, that goal is to show that F is sequentially continuous. And sequentially continuous is itself an implication, and that is the statement limit an equals x naught implies limit f of an equals f of x naught. So sequentially, so this is our goal, but our goal is an implication. And so in the context of, so for the purpose of showing that, then we will assume that the limit of an is equal to x naught. And then having assumed that, then of course, now we have a sub-goal, which is to show that the limit of f of an is equal to f of x naught. But that statement is itself an implication. Well, not an implication, but that statement itself can be unpacked. And so what does it mean to unpack that? For every epsilon greater than 0, there exists a cap n, such that for every n in the naturals, if n is greater than cap n, then notice here, this is applying to f of an and f of x naught, then f of an minus f of x naught absolute less than epsilon. So this is our goal now in the context of these other two assumptions. Now, how do we show that? that is a universal statement here for every epsilon, etc. And so it makes sense to let epsilon be greater than 0. And now once epsilon is shown to be greater than 0, then the goal here has to be to show that there exists a cap n. Now, epsilon is a positive number, and one of our assumptions, namely this one, gives us something that can be done to any, actually, I need to back up to this one. This assumption gives us something that can be done to every positive number. Namely, we can conclude that for every epsilon, well, this is true. And so using, let's number these now. Where can I number it? So let's call that 1. So using 1, there is some delta greater than 0 such that for all x in the domain of f, then this statement is true. So I'm just copying what we've assumed here. And so basically, I'm choosing delta so that that is true. Now, this assumption, which I did not fully unpack, is effectively the assumption that for any positive number, there exists a cap n, such that for every natural number n, if n exceeds cap n, then an minus x naught absolute is less than epsilon. And let's number that 2. That assumption 2 identifies that there is, that for any positive epsilon, well, for any positive number here, there is an n such that this is true. And so I can invoke 2 to choose such an n. So by 2, so there exists an n such that, and now I'm going to apply it to the delta, not the epsilon as before. So I'm going to apply this to delta. So there's an n such that for every n in the naturals, if n exceeds cap n, then this distance is less than delta, because I'm applying assumption 2 to delta, not to epsilon. Okay, so that gives me a cap n. Now, what do I need to show? So I've let epsilon be arbitrary, and now I've shown that there exists an n. And now, what is my goal? My goal is to show that for every epsilon, there exists an n such that this is all true. What is my goal about n? Well, let's identify a subgoal here. So we've gotten an n here. Now, at this point, my goal should be for every n in the naturals, n greater than n implies f of an minus f of x naught less than epsilon. Why should that be my goal? Because I've got the epsilon and I've got the n, and that should be my subgoal about what I'm trying to show about n. And so that's going to be my goal. And for the purpose of that goal, I'm going to say then what we should do is we should let n be in the naturals. And I'm going to do this all in one step. We're going to assume that n is greater than n. And then having done that, then I have a new goal, right? My goal was to show for every natural n, if this, then that. Now I've got an arbitrary natural n, and I've assumed this, so my subgoal is going to be this. So my goal is now f of an minus f of x naught absolute less than epsilon, and that has to now be my goal. Okay. N is greater than n. And so what do I know about about what happens when n is greater than n. I know this, so I'm going to invoke this. And that, let's call that 3. Okay, so I'm going to invoke this statement here. So this chooses an n and says that whenever n is greater than n, then this is true. And so by 3, what can we deduce here? We can say that since n is greater than n, then this is true. So an minus x naught absolute is less than delta. And now we have to go all the way back up to here. This actually, my numbers are going to be out of order, but this will be 4 then. So I have to go all the way back up to this statement. Remember, we said there is a delta such that for every x in the domain, etc. Now here, this statement, there is a delta, and I've chosen the delta such that, and then this is true about delta. Well, this is true for every x in the domain. So notice that an is in the domain of f. And notice furthermore that an minus x naught is less than delta. And so we can say by 4, so by statement 4, what do we get? We get this thing, f of x minus f of x naught absolute less than epsilon. And now we might say, oh, now we're done. But really what we should do is we should unravel what we've accomplished and show how the conclusions actually fall into place. So, so let's see here. It's a little detailed and I need to get my bearings here. So, so we need to demonstrate, first of all, that, well, the first thing we need to do is we need to make the right conclusion from this together with this together with this. So basically what I'm going to do here is I'm going to take these statements together and try to draw a deduction. Proof theoretically, we said let n be an arbitrary natural and assume that this is true. And then later, it doesn't matter how much later, then later within this context, we concluded that this was true. And again, I should have written an an here. I made the same mistake last time. So we have let n be an arbitrary natural. We have assumed that it is greater than n, and then we have proven this. And so this is called existential introduction. Sorry, that's called universal introduction. If we can let n be, well, it's actually an implication introduction too, because I did 2 things here. If n can be arbitrary here and assume this and then prove this, then what have we shown? What we've really shown is thus, for every n in the naturals, if n is greater than n, then f of an minus f of x naught is less than epsilon. So that's what we've really shown here. Now, however, so that's what we proved here. Here, we demonstrated the existence of an epsilon and then proved this about it. So if you can demonstrate, if you can choose an n and then say this about it, then our correct conclusion from that, so this is kind of like, this feels like a different kind of thing. I'm unraveling instead of raveling. So let's use a new color for this. So here I said there is an n. And so if we can say there is an n, and then we can say this about it, then what we have proven is we've proven there exists a cap n such that for every n in the naturals, etc. But before that, we chose an epsilon arbitrarily. And having chosen an epsilon arbitrarily, we proved this about epsilon. And so here, what we have effectively proven is thus for every positive epsilon, there exists an n such that for every n in the naturals, let's copy this line, n greater than n implies f of an minus f of x naught is less than epsilon. All right. So basically, so this final step is called universal introduction, but it's really just the argument that epsilon was arbitrary. And if I can prove something about any arbitrary epsilon, then I can conclude that it's true for all epsilon greater than 0. Now, what happened before that? So first of all, notice here that this is the conclusion that f of an converges to f of x naught. Now, what happened before that? We assumed that an converges to x naught. If you can assume this thing and prove this thing, then what you have effectively done is you've proven the implication. So from the fact that under the context of this assumption, I proved that, I'm going to conclude that this thing implies that, right? That's called implication introduction, and it's how you prove an implication. So again, we're sort of popping out of this list here. So thus, if the limit of an is equal to x naught, then the limit of f of an is equal to f of x naught. So that's an implication introduction coming from this conclusion as a consequence of this assumption here. Assume this. Now, so what does that mean? That means, i.e., so f is sequentially continuous, right? So this, if this limit, then this limit, that's sequential continuity. So basically, we've proven that f is sequentially continuous here. But under what assumption have we proven that f is sequentially continuous? Under this, the very first assumption. I should have drawn this one. So under this very first assumption, that f was epsilon delta continuous. So under this assumption, we have proven that f is sequentially continuous. What should we conclude? We should conclude by implication introduction, if f is epsilon delta continuous, then f is sequentially continuous. And that is finally what we were trying to prove. So this is, in a way, the same proof that I gave the first time, but it's an attempt to showcase how all of these logical pieces fit together. And they fit together in very complicated ways, but they fit together by means of very simple principles. If you want to prove P implies Q, you assume P, you conclude Q, you demonstrate Q somehow, and then you conclude P implies Q, which is implication introduction. If you want to show for all epsilon something, you let epsilon be arbitrary, you prove something, and then you do universal introduction, therefore for all epsilon. If you want to show there exists something, you demonstrate that you demonstrate that this one works, and then you do the existential introduction of saying, okay, I guess there is something. So all of these are basically sort of digging down into the details of this proof and then popping things back out so that we can get the right implications and the right universal statements here. So this is again the proof that if epsilon delta continuous, then sequentially continuous. Now we're halfway there, right? We've given true proofs, but they go in the same direction. Next, we need to demonstrate that if f is sequentially continuous, then it's epsilon delta continuous, and that'll be the next video.